The universe is a vast, enigmatic expanse filled with wonders that stretch the limits of our imagination. Among its most intriguing and mysterious inhabitants are the remnants of dead stars, neutron stars. These objects, born from the violent and beautiful death of massive stars, are like cosmic laboratories, revealing to us the hidden secrets of the universe. Their existence challenges our understanding of matter, energy, gravity, and time itself. But how do these strange objects form? And why are they so important? Stars are born from clouds of gas and dust, forming over millions of years as gravity pulls matter together. In their cores, nuclear fusion begins, the process that powers stars by fusing lighter elements into heavier ones, releasing an enormous amount of energy. This energy counteracts gravity, creating an equilibrium that allows stars to shine for billions of years. For most stars, this fusion cycle continues until they run out of fuel and fade slowly into white dwarfs or black holes. But for the most massive stars, those much larger than our Sun, their lives unfold much more rapidly and violently. These stars burn through their fuel in mere millions of years, exhausting their hydrogen much faster than their smaller counterparts. As these massive stars approach the end of their lives, the fusion process slows, causing the core to contract and heat up. The outer layers, still pushing outward, swell up, and the star becomes a supergiant. It's a time of extreme instability, as the core is no longer able to sustain itself. Eventually, gravity overwhelms the star's ability to hold itself up. The result is one of the most dramatic events in the universe, a supernova, a spectacular, cataclysmic explosion that can outshine an entire galaxy for a short period of time. What remains after this explosion is not just the remnants of a star, but a dense, gravitationally collapsed core, the seed of a neutron star. The core of the dying star undergoes a rapid collapse under its own gravity. As the pressure increases, the electrons and protons in the core combine to form neutrons. This is where the name neutron star comes from. The result is a star composed almost entirely of neutrons. Now, consider this. The neutron star that forms is incredibly dense, so much so that a single cubic centimeter of its material would weigh about 6 billion tons, more than all of humanity combined. The mass of the Sun is compressed into a space no larger than a city block, and the result is one of the most mind-boggling objects in the universe. These neutron stars are not just dense. They are so dense that they warp space-time itself. The fabric of the universe bends and twists around them, creating a gravitational field so intense that even light cannot escape from it once it gets too close. This point is known as the event horizon, the boundary beyond which nothing can return. If you were to fall toward a neutron star, you would be stretched and compressed in a process known as spaghettification. Your body would become a thin, elongated strand of matter as you neared the star. The gravity near a neutron star is more than 2 billion times stronger than that of Earth. To put this into perspective, imagine being able to lift a skyscraper with your bare hands, or feel the crushing weight of an object that weighs as much as a mountain pressing down on you. This is what it would feel like standing near the surface of a neutron star. But the neutron star's influence doesn't end with gravity. These objects also possess some of the most powerful magnetic fields in the universe, often 1,000 times stronger than those of typical magnetized objects. These magnetic fields channel charged particles into narrow beams, accelerating them to nearly the speed of light. The result is an emission of radiation, X-rays, gamma rays, and sometimes visible light, that can be detected across vast distances of space. In fact, these magnetic fields are so intense that they can distort the behavior of matter in ways we're still trying to fully understand. The charged particles accelerated in these fields can interact with the surrounding material, creating cosmic jets, streams of material blasting away from the poles of the neutron star at nearly the speed of light. These jets emit intense radiation, visible to telescopes billions of light-years away. Now, add to this the rapid spin of a neutron star. Some neutron stars rotate hundreds of times per second, an unimaginable speed. These stars, known as pulsars, emit regular pulses of radiation as their beams sweep across space, similar to the beam of a lighthouse sweeping across the shore. This is why pulsars are often described as cosmic timekeepers. Their pulses so precise that scientists have used them to measure the fabric of space-time with unprecedented accuracy. The regularity of these pulses is so exact that they allow astronomers to detect minute changes in the universe, like the presence of gravitational waves, which ripple through space-time when massive objects, such as black holes, collide. Pulsars have even helped confirm Einstein's theory of general relativity, providing the most accurate tests of his ideas in extreme environments. But pulsars are not just fascinating for their regularity. They also serve as a laboratory for studying the most extreme conditions in the universe. Their regular pulses are not only a cosmic clock, but they reveal the nature of space-time itself. For instance, when a pulsar's signal passes through different regions of space, it can reveal the presence of interstellar material, gas, dust, or even the effects of gravity from unseen objects. Astronomers have used pulsars to detect the bending of light due to the curvature of space caused by massive objects, and in doing so, they've confirmed the existence of black holes, neutron stars, and even dark matter, all with unparalleled precision. But pulsars and neutron stars don't exist in isolation. They interact with the interstellar medium, the gas and dust that exists between stars, affecting the dynamics of galaxies themselves. These interactions can shape the formation of new stars, stir up cosmic clouds of gas, and even influence the birth of new planetary systems. Neutron stars are not only remnants of dead stars. They are cosmic engines, driving change and shaping the very environment they inhabit. Some neutron stars are part of binary systems, paired with a companion star, and they can siphon material from their neighbors. As this material spirals into the neutron star, it forms an accretion disk that heats up to extreme temperatures, emitting X-rays and other forms of radiation. In some cases, these systems can produce dramatic phenomena like X-ray bursts or even gamma-ray bursts, the most powerful explosions in the universe since the Big Bang. And when two neutron stars collide, the result is even more dramatic. These mergers can produce ripples in space-time, known as gravitational waves, detectable by observatories like LIGO. The collision itself can also create heavy elements like gold and platinum, making neutron star mergers key players in the cosmic formation of these precious metals. These events, rare but profound, remind us that the universe is an intricate and interconnected system, where the death of one star can give birth to new elements, new stars, and new insights into the nature of the cosmos. Neutron stars are more than just remnants of dead stars. They are cosmic beacons, carrying the imprints of the universe's most violent processes and illuminating the deepest questions we have about the nature of matter, energy, and gravity. They are symbols of the cosmic cycle, where destruction leads to creation, and the end of one phase births new possibilities. As we look deeper into the mysteries of neutron stars, we come to understand that these strange and powerful objects are not just markers in the night sky. They are windows into the fundamental workings of the universe, holding within them the answers to questions we have only just begun to ask. In the endless expanse of the cosmos, neutron stars are reminders that even in death, the stars leave us with the greatest gift of all, the chance to learn, to explore, and to uncover the secrets of existence itself.